So, all right, so is this clear? So, so in the radial direction, the exponential map preserves lengths of tangent vectors. So this will be equal to, this integral will become just the integral from 0 to 1 of mod of inner product C tilde prime t C tilde t over norm C tilde t dt. And now notice what I have here, this inner product divided by this norm, this thing in a vector space, since we're working, this is the inner product in the tangent space. So note what is ddt of norm C tilde t. So this is ddt of inner product C tilde t C tilde t to the half. So by the chain rule, this is half inner product C tilde t C tilde t to the minus half into 2 times inner product C tilde prime t C tilde t, right? Which is equal to exactly this half, and the 2 cancels, and this becomes 1 over the norm. So this becomes exactly inner product of C tilde prime t with C tilde t over norm C tilde t. Right? Is this clear? Yes?
Yes.
So this integral is greater than the integral without the mod. So this is greater than the integral of just this without the mod. C tilde prime t C tilde t over norm C tilde t. And this is equal to the integral now of ddt of norm C tilde t dt. And so now by the fundamental theorem of calculus, this is equal to norm of C tilde 0. Okay. Which is equal to norm V, where XPV is equal to, sorry, not C tilde 0, C tilde 1. C tilde 0 is 0, so this will be C tilde 1. So XPV is equal to gamma 1 is equal to C of 1 And we've already shown that norm V is equal to the length of gamma, right? This calculation we already did. Gamma is the geodesic XTV, right? Is this clear?
Yes, sir.
Yes, any questions? Is this all right up to here?
Yes, sir.
Okay. Now, so this we did assuming that that the curve stays inside this geodesic ball, right? We did this assuming the curve stays inside the geodesic ball. But if the curve goes outside the geodesic ball, then the argument is very easy, because if it goes outside the geodesic ball of radius epsilon, then the same argument breaking into normal components and so on will tell you that the curve has length at least epsilon, right? Because you take the curve, the part of the curve which, look at the first time it goes outside the ball, then the part of the curve from P up to the first time it goes outside the ball, I can apply the same argument and I'll get that the length of that part of the curve is at least epsilon, right? And so then the total length will be greater than or equal to epsilon, and epsilon is greater than or equal to the length of gamma, right? Because gamma is a geodesic in this ball starting from P in this geodesic ball of radius epsilon. Is this clear? So then the length will automatically be bigger than epsilon. Is it clear?
Yes.
Okay, so maybe I'll just write that down. So I'll just write that down, and that will finish the proof. So if C is not contained in B, okay, let me just write here. So we are done if C is contained in B, and if C is not contained in B, let T naught equal to the inf of, oh sorry, the inf of T positive such that CT does not belong to B. Okay, so this is positive because for small t, the by continuity CT belongs to B, and so then CT naught belongs to boundary B. And C restricted to 0 T naught is contained in B closure. So then length of C, this is greater than or equal to length of C restricted to 0 T naught. And this, by the same argument as before, this is greater than or equal to epsilon by the same argument as above, using, so because this is contained in the ball, I can define C tilde is equal to F inverse composed with C restricted to 0 T naught. Is this clear? And this is greater than or equal to the length of gamma. So we are done. Okay, so that finishes the proof. Is this all right?
Yes, sir.
Okay, so I made a little, I made a few simplifying assumptions. I assume the curve was C1 and so on, and it doesn't pass through the origin except at time t equal to 0. But you can, if it's piecewise C1 in general, so then you'll have to apply the same argument, breaking it up into intervals where it is C1 and so on. Okay, but I mean, it's not much more difficult. Do you understand? If it's piecewise C1, you can just break it up into intervals, and then again, you apply the fundamental theorem of calculus in each of these intervals, like we did here. Okay. At some point, we use the fundamental theorem of calculus, right? At the last step. So that's what you do here. In this last step, this integral ddt of norm C tilde t. So there you use the fundamental theorem of calculus, and then you add up over the intervals, and then you'll get what you want. Okay. Is it clear? Yes?
Yes.
Okay. This is fine. Yeah. And if it passes through the origin, then you break it up into the intervals where it is non-zero, this C tilde, and then you integrate over those intervals and so on. All right. So these are some small modifications you have to do. That's all. Do you understand for the general case?
Yes, sir.
Okay. So I'm not doing that. So I think this is a good place to stop. All right. So any questions to finish? Okay, so the picture is that if I take a geodesic starting from a point P, then for small time between P and so P is say gamma 0, and say let's say for gamma, suppose it's unit speed. So then for t small enough, from gamma 0 to gamma t, gamma is the shortest curve joining these 2 points in the whole manifold, gamma 0 to gamma t. Is that clear? Okay. Right. So therefore, geodesics are locally length minimizing. Geodesics are locally length minimizing. All right. So the one thing we haven't proved is the Gauss lemma. I'm not proving it now because we'll develop the tools to prove more general statement later. So about when we come to the structure of the tangent bundle, it'll just follow as a corollary, the Gauss lemma. When we talk about the derivative of the exponential map using what are called Jacobi fields, it will follow as a simple corollary. So any questions? Anyone? Utsav, Bappa, Orkojit? Any questions? Since I know that you sometimes ask questions.
No question.
Okay, it's clear?
Yes.
Okay, all right. Okay, thank you. So let's stop today then. And I'll see you next week. Okay.